Designing macroeconomic policy is a high-stakes problem of mechanism design. You are trying to engineer rules yielding a desired social outcome, but you must deploy those rules inside a massive, highly interconnected, completely unpredictable system. Take optimal taxation. The specific task is predicting exactly how boundedly rational human agents will adjust their behavior when the structural incentives shift. Classical economic theory has struggled to solve this because the math quickly becomes too complex to remain analytically tractable. To make the equations work, classical models are forced to rely on simplified, static, one-step economies that ignore the realities of human interaction and time. This creates a vulnerability known as the Lucas critique. It dictates that historical data curves inherently fail to predict future behavior, because the moment you introduce a new policy, the underlying behavioral incentives of the economy change. Purely analytical, static mathematical models cannot map dynamic human economies. To optimize policy, we require a computational approach that tests policies directly against adaptive human behavior. To solve this, researchers developed the AI Economist, a computational framework built to bypass the analytical constraints of the Lucas critique. The system operates on a two-level deep multi-agent reinforcement learning architecture. At the top level, a macro planner observes the market and sets taxes. At the micro level, autonomous agents observe rates and independently allocate labor. Both learn simultaneously. The planner updates policy to optimize social welfare, while agents continuously adapt to maximize personal utility. By pitting the planner against the agents inside a simulated, evolving microeconomy, this two-level architecture empirically tests millions of policy combinations. To prove the validity of the framework, researchers built a micro-founded spatiotemporal testing environment called Gather, Trade, Build. Agents move across this grid to gather resources. They can trade those resources through a continuous double option or use them to build houses. Building generates income based on a Pareto distributed variable called build skill, leading agents to naturally specialize over time. The state of the environment is tracked mathematically as a three-dimensional tensor, mapping the physical grid dimensions against the unique entities occupying each cell. This schematic outlines the asymmetric design of the simulation's observation spaces. Agents have a private state and only observe their immediate egocentric spatial window. The planner is blind to individual skills. It only observes the public state of global market behavior and aggregate endowments. Look at the lower pathway. Each agent processes its spatial data using a neural network stack flowing from a convolutional neural network into an LSTM. They output one of 50 discrete actions, strictly seeking to maximize their own isoelastic post-tax utility, a model where their satisfaction diminishes as they earn more money, but the cost of their labor scales linearly. On the upper pathway, the planner uses a separate MLP LSTM network to process the public state and dictate rates across 7 tax brackets, explicitly designed to maximize utilitarian social welfare. Setting up these asymmetric, blind constraints forces the AI agents to act strictly as boundedly rational actors, establishing a mathematically rigorous proving ground. But running this simulation reveals the primary technical hurdle of simultaneous multi-agent reinforcement learning. The environment is highly unstable and non-stationary. It is a nested optimization problem. Conceptually, the agents are trying to solve a maze, while the planner is actively redrawing the walls. Mathematically, these objectives collide. An agent's utility, U, strictly depends on the exact tax rates, tau. But the planner's policy, pi p, which sets those tax rates, is updating simultaneously.
In early training, this leads to an immediate failure state. An untrained, randomized planner will suddenly output highly punitive tax rates while the agents are still learning how to move and work. When an exploring agent performs labor, it incurs massive negative utility from the effort. If a random tax policy then wipes out its entire income, the agent quickly learns the optimal choice is to do nothing, completely destroying the learning gradient. A standard deep reinforcement learning setup inevitably self-destructs here. The macro planner accidentally punishes the exact micro-agents it relies on to generate its data. To prevent this policy collapse and stabilize the system, the AI Economist relies on 2 specific engineering interventions. The first is structured curriculum learning. The simulation phases in labor costs early and slowly introduces tax rates only after the agents understand how to work. Even with a curriculum, the co-adaptation process is incredibly volatile. This graph tracks social welfare metrics. You can see how the blue line, representing the AI Economist, experiences massive early oscillations and steep dips as the planner tests policies. The second crucial fix is entropy regularization. Notice the point right around 300 million steps, where the blue curve finally stabilizes and steadily climbs. Entropy regularization forces the planner to maintain a highly random entropic policy during early training. This intentionally exposes the agents to a wide distribution of possible tax rates, forcing them to learn robust economic strategies rather than collapsing under a single punitive model. Intentionally delaying the planner's true optimization until the entropy coefficient anneals completely solves the non-stationary co-adaptation problem. The agents learn to survive, enabling the planner to learn how to govern. With the system stabilized, the researchers evaluated the AI Economist against classical optimal tax theory.
The standard baseline is the SAS model, a mathematically proven optimal tax formula widely used for static, one-step economies. This chart shows marginal tax rates tested in a simplified one-step environment. The blue line of the AI Economist almost perfectly maps to the yellow schedule of the SAS formula. Because the deep reinforcement learning system independently derives the absolute mathematical limit in simple environments, its findings in complex settings are a direct computational extension of that proven logic. The true test comes when both the AI Economist and the SAS model are deployed into the complex, multi-step gather, trade, build economy. Complex rational behaviors immediately emerge, completely unprompted by human coding. Agents naturally form specialized trade networks between top-tier builders and lower-tier gatherers. The RL agents also discover intertemporal tax gaming. Panel C tracks agent income across 10 tax years. Notice the erratic spikes. High-skill agents halt labor to drop into lower tax brackets, successfully reducing their burden versus a smoothed approach. In Panel B, rising top tax rates depress stone prices, destroying low-skilled gatherers' income. This is exactly why the mathematical SAS model fails in the gather-trade-build environment. Its formulas inherently assume that behaviors remain static and independent. The final divergence between the formulaic tax and the AI-generated tax is stark. In Panel C, across multiple spatial layouts, the blue columns representing the AI Economist achieve a statistically significant higher utilitarian welfare than the yellow SAS baseline. The AI discovers a superior, highly non-intuitive tax schedule precisely because it accounts for network interaction effects and intertemporal tax evasion. By knowing actual adaptive human responses rather than static equations, micro-founded reinforcement learning functions as a scalable method for designing economic policy, optimizing for the interconnected realities that pure mathematics cannot map.